Okay, welcome to lab. So as I mentioned earlier, we're going to continue lecturing for a little bit, just to kind of get us back on pace. And we'll probably take us a little break and we'll come back and we'll talk about today's sort of experiment, which is activity 1, which should be Excel and stuff like that. So again, make sure you put here in the chat box for roll as well. Again, in both lecture and lab, just do that at the beginning. So you got it there. Get counted. All right. So a couple of things as well. I did put up on our Canvas site and sent out an announcement as well in regards to, excuse me, a Proctorial practice quiz. So make sure that you do go and take that. Again, that will kind of give an idea if you haven't used Proctorial as a proctoring sort of device, how it all works and get it all worked out before we maybe use it for something. Again, we may use it for proctoring for quizzes and exams. We may also do it through Zoom as well, but I just want everybody to go through it. It's basically just going to be counted for completion, gives you an opportunity to, again, to make sure your computer's set up to use it if we do use it, and how it kind of works, and also uploading obviously an assignment as well from it, and get your camera sort of set up the way you need it, hopefully for a quiz and lecture. So I think you have until the end of this week or something like that to do that. So make sure that you do complete that. And again, in case we do end up using it sometime throughout the semester, you're not trying to figure it out on the day of like a quiz or an exam or something like that. Let's see, there's that. All right, so as I mentioned before, we're going to continue lecturing a little bit. Then we'll stop, take a little break, and we'll come back and talk about the activity. And other than that, I think we did the last example. So why don't we continue on then, and why don't you give this example a go here. So take a couple of minutes here and work on this one. Here we are looking for the equilibrium pressure given the information that's provided to you, and see what you come up with, and then we'll go through it together here in just a minute or so, a couple minutes.
Professor,
Yeah.
is it supposed that the partial pressure for nitrogen oxide to be two different values?
It is. So there is. Let me give you the right one. They both say NO. One should say NO2. Let me just take a look here and try to figure out which one should be which. I believe the NO2 is the 0.4 one. So the 0.4 should be the NO2 here. We get something to write with here. Put that up there for you.
Thank you.
Yep. Thank you. So this guy here should be the NO2. There we go. And the other one is the NO. Might make it easier to solve, I imagine. Also given a Kp value of 158 and some pressures. So we definitely would want to start with our Kp expression. So remember, it really is the same thing no matter sort of what equilibrium expression. It's going to be products over reactants. Here we would take the partial pressure and we would want to square it for NO times the partial pressure of O2. Again, we're squaring it because of the coefficient. Coefficient here is obviously 1, so we don't have to worry about it. Divided by the partial pressure squared of NO2. Again, we're squaring that one as well because of the coefficient that's present there up on top. That's going to equal a 158. Now that we know which one's which, we could actually put it in. So our NO, which is 0.270 squared, times the partial pressure of O2, would be divided by our 0.4, also going to square it, equals 158. Mathematically, we're going to multiply that to the right-hand side. We're going to divide by the 0.27 squared. So we will end up with the partial pressure of O2 equals 158 times 0.4 squared. then we need to divide it by 0.27 squared. Again, multiplying the bottom, dividing by the top to the other side. Do all that good stuff there. I think you end up with 347, and it would be atmospheres here. You do need units because we're not looking for the equilibrium constant, but we are actually looking for a pressure. So the units would be obviously the same as everybody else's units that are present there. Any questions on that calculation? Also does sort of make sense if we just think about what we see in terms of our Kp value. Our Kp value of 158 is a relatively large value, which would pretty much imply this reaction is heading to the product side. And we would have a lot of products at equilibrium, including O2, which clearly is supplying a good amount of pressure at that point because it is present. Any questions on where any numbers came from, why we did anything?
Yeah, I had a quick question about the equation. So because we have the value of K or the Kp, that's why we use this equation. But if we were trying to find Kp, then we would use the Kc parentheses RT with delta N.
So in this particular one, we're trying to find the partial pressure of this guy, and we're given the pressures of everybody else. So that, and also the Kp value, which is why we use the Kp expression. If you were asked to calculate what the Kp value was, you would either have one of two ways of doing that. Either you would have all of the partial pressure values and you would just put it into this expression here, kind of plug and chug into that expression if you had them all. Or alternatively, if you had, say, the Kc value or just concentrations given to you, you then could use that other equation that we saw by first calculating Kc and then getting to Kp. In this particular problem, you didn't have enough information to use this one at all because obviously you didn't have all the pressures. Otherwise, you could just calculate Kp directly, and you didn't have all concentrations, so you couldn't calculate the Kc value. Other questions on that?
I'm a little bit confused by the wording. So P stands for partial pressure, correct?
It does.
Yeah. So why is it asking for equilibrium pressure? Is it the same thing?
It is. So remember that basically, so a lot of times, you know, when we think about equilibrium, we think about, you know, the reaction or the equation. There's like a left side, right side reactants product. But ultimately, if you have this reaction sort of happening, pretty much everybody's in the same container, right? You got NO2 guys flying around, you got NO flying around, you got some O2 flying around. They're all basically in there. There's really no sort of left side of the equation, right side inside the flask or anything like that. They're partial pressures because whenever you have a mixture of multiple gases together, they each contribute to a part of the overall pressure of that entire container. And it's going to eventually, once they're all in there, at some point, even though they're all flying around in there, it is going to reach a state like we talked about earlier, where that forward reaction will equal that reverse reaction. And at that point, it's basically going to be whatever their pressures is at that point is going to be their equilibrium pressures. And it's also going to really be still considered a partial pressure because each of those gases are not flying around in there by themselves. So there's other gases in there and stuff like that. So they're each sort of contributing. So it's sort of the same thing in the sense that the equilibrium pressures will be the partial pressures of each the gas. Basically, when that overall reaction hits that point in terms of backwards and forwards, in terms of the rate, equals each other.
Thank you.
You're welcome. Other questions? Okay. So, you know, you want to make sure that, you know, some of these problems you can only sort of solve in certain ways because you're only given a certain amount of information. And that's why, you know, we have sort of that formula, that Kp to Kc formula that allows us, you know, in case we're just given, like in the previous example, just say concentrations, we could get pressure, the Kp from that using the Kc value. All right. Hopefully they agree with us. There we go. All right. So we talked a little about homogeneous equilibrium, and it doesn't always happen that way. Obviously, a lot of reactions involve mixtures of different sort of states, and that's what is referred to as heterogeneous equilibrium. And basically, just like a heterogeneous mixture, you see different phases and stuff like that. Here we have everybody, or a lot of guys, in some different sort of phases. We have solids, we have gases, and stuff like that. So we can approach it the same way by taking our products over our reactants. As we talked about earlier, if we have something that's a pure liquid, it's really not going to affect the equilibrium. And solids, as well, as we'll see here, will not have an effect on the equilibrium. They're basically, if you want to think about it, they're kind of just like sitting, like if you threw like a rock into a water, basically, or a beaker of water. Maybe don't throw the rock, but drop the rock into a beaker of water. You know, that rock is really not going to do much other than sink to the bottom and basically sit there as decoration. And that's sort of what happens in these sort of equilibrium reactions. When we have solids involved, they really remain constant. They're not really interacting. So much like liquids, as I sort of mentioned earlier, we're not going to include those guys in the equilibrium expression. And essentially, if we were to write the equilibrium expression for this particular reaction, it would actually look like what I just boxed. It is the Kc would be our products. And in this case, it is only the CO2 that's a gas that really will be participating. The calcium oxide, the calcium carbonate is really not participating. They're both solids. So it's products over reactants. So since we don't really have reactants here, it's basically CO2 over 1, which is the same as CO2, right? So this would be our proper equilibrium expression for concentration. Because CO2 is a gas, you can write a Kp, which will look like this. Kp is equal to the partial pressure of CO2 in this particular case. So it just sort of goes back to what I kind of mentioned a little bit earlier, that if you have anything that is solid or liquid, you do not include them in the equilibrium expression. So as we talked about previously this morning, that pretty much leaves you your aqueous and your gas, and those are the two that should be included, and really the only ones that will be included. And obviously, as you can see here, if there is, you know, the reactants are all solids or the reactants are all liquids or whatever it may be, we just basically do the products. If you had a reaction where it was something like this, and maybe you had a solid or a liquid on the product side, if you were to write the K, it would be 1 over concentration of A times the concentration of B. So, you know, that's sort of how you would handle it if you had, say, on the product side, everything that's not included, you just do 1 over your reactants if you're going to write the expression in that particular case. Yeah.
If CaO was like a aqueous, would be included?
Yeah, so if the CaO was aqueous, it would be included. Yep. In the Kc. Yep. Other questions? Okay. So here's just sort of graphically what we're talking about. Here's sort of this reaction. And you can see basically those solids are essentially just sitting, you know, kind of on the bottom, not much, you know, really participating or anything like that. In order for those solids to really participate, you know, for example, it has to dissolve and become aqueous. And if it became aqueous, then it obviously would be aqueous at that point, no longer solid, and you would treat it as aqueous. Same thing if it maybe decomposed into a gas, then it obviously would be a gas at that point and it would be included. But in its solid state, it really will not participate. The pressure of what's going on doesn't really depend on, you know, how much solid and stuff like that is present. All right, want to try another one here. We want to calculate both the Kp and Kc in this case. Partial pressures of everybody is 0.265. So take a couple minutes to see what you come up with. Okay, so let's see how we're doing. So here again, we want to calculate both the Kp value and also the Kc value. So again, in these problems, you want to kind of look at and kind of see what information is given to you. In this particular case, we're given pressures. So Kp would make sense to solve for first. So if we write our Kp expression, again, going to be our products, which is the partial pressure of NH3 times the partial pressure of our H2S. And here are reactant is a solid, so we would not include it. So this would be our Kp expression. Since each of the gases have the same pressure, that makes it pretty simple. We're just going to plug that number in there twice. And it looks like perhaps we end up with 0.0702. Again, this being our Kp value, we don't need units or anything like that associated with it. It is just a number. Any questions on the first part here? Now, since we now have the Kp value, we can use the formula that we saw earlier to allow us now to get to the Kc value, which would be RT delta N. So much like before, we had a couple of things we need to kind of figure out. First off would be delta N, which is the number of moles of gas molecules. Again, taking our products minus our reactants. So this is going to be 2 minus 0, which is 2 in this case. Again, 2 gases on the right-hand side, just adding up the coefficients, and no gases on the left-hand side there. Again, that's a solid. Lastly, temperature already in Kelvin, so we're okay on that. So we can basically go with 0.0702 equal our Kc, our R, which is our gas constant, our temperature, which is already in Kelvin, and again, we're going to square that. So we basically can clean up the right-hand side there, 0.08206 times 295. We also want to probably square that as well. That's going to give us, call it 586 and some change. So 0.0702 equals Kc 586.0127. We'll take it a few numbers. We're going to divide this to the other side there, giving us a Kc value of, looks like 1.20 times 10 to negative 4, looks like.
Where did you get the to the power of 2?
So that is the delta N, which is the difference in the moles of gas molecules on the products minus reactants. So product side, this is a gas molecule, it's just 1, and that is 2, so that would be 2. On the reactant side, that's 0 because that's a solid. So
If the solid was a gas, would it be 1 then?
it would be in this case. If it was a gas, you would obviously do 2 minus 1 in this particular case.
Thank you.
Yep. But you do want to make sure, again, sometimes people go automatic on that and they just go by whatever's there. You do want to make sure you do look at the states and make sure that, they are gases. Yeah.
If there was any coefficients in front of that, would that also cause the equation for delta N to be different then?
So Samantha, you're asking like if this was like a 3 or something?
Yeah.
So if it was a 3, you would. So if let's just say, for example, that was a 3, then on the product side, it would be 3 and 1, which would be then 4 minus 0. It would end up being 4 in that made up example.
Okay. Cool. Thank you.
You're welcome. Other questions?
Professor, isn't it to the power of negative 3?
I'm sorry?
Isn't the answer to the power of negative 3?
Let me double check. 1, 2. I got to the negative 4. On my calculator, I got 0.000119793. Yeah. So 1, 2, 3, and 4. I hope. Let me punch it in one more time just to make sure, but I think.
Oh, it's my bad. I forgot a 0.
Okay. No worries.
Sorry about that.
Yep, no problem. Any questions?
Do we
Okay.
have to write our answers in the scientific notation?
The question is, do you have to write your answer in scientific notation? The answer is you don't have to unless it specifically says to do so. Again, you should try to write your answers to the proper number of sort of sig figs and stuff like that. So sometimes it's easier to kind of put it into scientific notation. But if you want to write 0.000120, that's perfectly fine as well. Again, only unless it's specifically said, put the answer in scientific notation, and then you can do it. But as you know, hopefully sometimes there's a lot of zeros and stuff like that. So sometimes it's good to kind of do that. Other questions? All right, questions on how to calculate KP, KC, KP from KC. Any questions on any of that stuff there? As I think I mentioned before, you are responsible for formulas and stuff like that. So obviously, like the one we use here, you do need to know it. Okay. All right, then let's talk about equilibrium constants, and sometimes the way we may have to manipulate the equilibrium value to find other values that we need. So for example, if we have these two reactions here, A plus B goes to C plus D, and that particular reaction has an equilibrium expression for it specifically, which is this guy here. And if we have another reaction, C plus D goes to E plus F, and if we wrote the equilibrium expression for just that second reaction, that would be the guy on the right. As you may know, maybe when you did something like everybody's favorite, like Hess's law, adding all those equations together to get an overall equation, and you have to adjust like your delta H values depending on sort of what you did. That sometimes happens with equilibrium constants. So sometimes we have an equation that we are looking to determine what the equilibrium constant is, but we may just have individual reactions that will allow us to get there. As you probably again learned it with Hess's law, you know, sometimes reactions don't always occur sort of in a one-step process. It may be multiple reactions that occur to sort of get you to the overall reaction that you're looking at. So if we were to add both of these reactions together, the C and the D would cancel out, and they would cancel out again opposite sides of the arrow. They will basically cancel each other out. They're almost like equal signs, right? And we're left with A plus B gets us E plus F. And if we wrote a K value for that, we would end up with this expression here. So when we're dealing with equilibrium reactions and we're looking, for example, let's just say we did not know what this number was, the K value, and we're trying to find it, but we did know both of these guys, we can very easily find the value of the K for adding those two reactions together by, it's actually multiplying these two. So if you multiply these two things, this K expression here by this K expression here, these guys cancel, leaves you E times F over A times B, which is this guy here. So one very common manipulation that we do with multiple equilibrium reactions is if we add them together, those reactions, and we cancel out whatever cancels out, we then multiply the K values together. And when you multiply the K values together, that will give you the K value for the reaction you're looking for. So sometimes people always want to add those K values together, but you're actually going to be multiplying the K values in this particular case. Any questions on that? Now, another very common sort of process that occurs is also something that you probably did when you played with Hess's law, is sometimes you don't necessarily need the reaction the way it's written. Sometimes you need the reverse of the reaction. So you need like the reactants on the product side, products on the reactant side. So sometimes you have to reverse an actual reaction. And how that affects the K value is, as we see here, when we reverse a reaction, basically our reactants become our products and our products become our reactants. So it is really the inverse of the K value. So 1 over the K value. And that's what we see here. Basically, our product is NO2 in this reaction, and our reactant is N2O4, gives us a K value of 4.63. If we reverse the reaction, our products become our reactants, which means it ends up on the bottom, and our reactants become our products, which means it ends up on the top. And that is basically the inverse of what we have on the left-hand side. 1 over the K value gives us 216 in this particular example. So that's a very common way. If you need to reverse a reaction, the K value actually becomes 1 over the K value. Not like a lot of people think, like, hey, I'll just make it negative and positive. That's not how it works here with K values. It ends up being 1 over the original K value in that particular case. Question on that there. Other common things that you sometimes have to do. So for example, let's just say we had this reaction here, A plus B goes to C plus D. And basically, if we write the K for this, this is C times D, A times B. Now, let's just say that we do not need one of everybody here, but we actually need two of everybody here. So something also like you did probably with Hess's law is sometimes you have to multiply by a common number. And if you multiply this by a common number, we will end up with a K value that is C squared D squared divided by A squared and B squared. And if you look at what is the difference as we go from the top reaction to the bottom reaction in terms of the K value is we squared it. So we multiplied by 2, we basically squared the K value. So we take the K value and we square it. If I multiplied by 3, it would end up being cubing it. You would then cube the K value. Multiply by 4, take the K value to the 4th power, and so forth. So another very common sort of manipulation is if you multiply the reaction by a common number, you take the K value to that common number. So you take the K value to that common number up on top. Now, sometimes you may start with 2 of everything, but actually only need 1 of everything. So basically what we would be doing in that particular case is going from the bottom reaction to the top reaction. And if we were going from the bottom reaction to the top reaction, as we go from our K value, from the bottom K value to the top K value, the difference is actually it is the square root of K. We divided by 2 basically all the way across, so we take the square root. We divided by 3, we would take the cube root, divided by 4, take the 4th root, and so forth. So if you need to manipulate by dividing by a common number, you basically take the K to that common number, basically. And so those are like probably the 4 most common sort of manipulations that you sometimes have to do. Again, this would be a situation where you're given multiple sort of equations, multiple K values for those equations, and you're asked basically to come up with a K value for an overall equation by manipulating each of those sort of individual reactions. So again, this is very similar to kind of what you did if you remember Hess's law. The difference is, though, how we deal with K values is very different than, say, delta H values here. So just to review here, if we take a K value and we're trying to find it by adding multiple reactions together, we multiply the K values. If we reverse a reaction, we take 1 over the K value. If we need to multiply by a common number, we take the K value to the common number as the exponent. And if we need to divide by a common number reaction, the K value is taken to the root of that common number. Any questions on those manipulations there? Okay. So a couple of things that we've talked about up to this point. Typically, when we talk about equilibrium, we're usually talking about them in terms of either concentrations, which is typically molarity. So that's usually what you want to use for concentrations is molarity. And if we're dealing with pressures, as I mentioned earlier, especially as we get a little bit more into this chapter, and I mentioned it before, if it is a pressure, make sure that it's in atmospheres when you're doing the calculation. And again, you can convert it to whatever other unit you may need after that. As we saw earlier, solids and liquids are not included in the equilibrium expression, so you don't have to worry about those. Also does not have units. The equilibrium value, just a number, which tells us if we have a large value for it that we mainly have products at equilibrium. If we have a small value, we mainly have reactants. The equilibrium value that we see is specific for exactly how the reaction is written, whatever is on the reactant side and whatever's on the product side, and the temperature. So again, temperature is the only thing that will affect the value of the equilibrium constant. And what I mean by that is if you took it from 25 to 50 degrees Celsius, the two values of K would be different. But if you took it to 50 degrees and kept it at 50 degrees through all your reactions, the K value should be the same for all those reactions at 50 degrees. Again, it only changes when you change the temperature. And as we talked about before, a couple of different ways to manipulate it. If we're adding multiple reactions together, make sure you multiply the K values, don't add them, reverse them 1 over the K value. And obviously, as we talked about there. Any questions on how to manipulate K values or any of that type of stuff we talked about? And this, what's on this slide here is something, again, that people do have a very difficult sort of time with, which is the idea that, you know, again, even if you started with very different amounts of reactants in a whole bunch of different experiments, regardless of what you do, as long as that temperature remains constant, that ratio of products to reactants should end up being about the same value. Again, that's the idea behind the equilibrium constant. Any questions on any of those things? Okay, then let's talk about another letter that will pop up here and there as we go throughout this semester here, and that is actually Q. And Q is the reaction quotient. So when we talk about Q, that is basically the reaction quotient. And what is the reaction quotient? Well, the reaction quotient is calculated the exact same way you would calculate K. So if you had our reaction that we've seen, this kind of generic guy, if I wanted to calculate Q, it is still our products divided by reactants. You would still take the coefficients as the exponent. So whatever the coefficients were, just like you would do with K, is calculated the exact same way. So you may say to yourself, if it's calculated the exact same way, what's the deal with the different letter? Well, they wanted a different letter, I suppose, other than K and everything. But the real difference is we use Q in a situation where either we know this is sort of our initial amounts of everybody, or we're not sure we're at equilibrium. So we can calculate Q to help us decide really those sort of two things. In a traditional Q type problem, you would do it and you would calculate to determine, first off, are you at equilibrium? And second, if you're not at equilibrium, which way you need to go to get to equilibrium. So in a sort of a true sort of Q problem, that is ultimately, you know, what you're trying to figure out is A, are you at equilibrium? And B, if you're not at equilibrium, which way do you need to go to actually reach equilibrium? And what we mean by that is, do I need to go to the right, which means I need to make more products to reach equilibrium? Do I need to go to the left, which means I need to make more reactants to reach equilibrium? That is essentially what we use Q for. Clearly, in order to calculate Q, and since it's calculated the same way as K, you need to have the concentrations of everybody or the pressures of everybody in order to actually calculate it. So that's one really big sort of hint as to whether or not you should perhaps calculate Q, is you're given the starting amounts of everybody, or you're given the amounts of everybody. And what I mean by that is you're given the amounts of the reactants, given the amounts of the products. And if you're given the amounts of the reactants and products, that would imply that obviously the reaction is happening, is taking place. So maybe you're not at the start of the reaction. Maybe the reaction is at equilibrium. Maybe it's on its way to equilibrium. And that's why we have the starting amounts of everybody. So the way that we can basically figure that out is to take the Q value that we calculate and compare it to the K value. So if you put all the Q's together on the left-hand side and the K's on the right-hand side, if Q is greater than the K value, that essentially means that you are A, not at equilibrium, And to reach equilibrium, you need to actually go to the left and make more reactants. So you could think about it opposite the way that points. If you kind of go back this way is the way you need to go. You need to go back to the reactant side to reach equilibrium. If you calculate Q and it equals the K value, then congratulations, you are at a system that is at equilibrium at that point. And lastly, if you calculate Q and it's less than K, that tells you that you are not at equilibrium. In order to reach equilibrium, you need to go opposite the way this thing is pointing towards the right-hand side and make more products to reach equilibrium. So in a traditional sort of Q value or Q problem, this is ultimately what we're looking to try to figure out is whether or not, we obviously see that we have a certain amount of reactants, a certain amount of products that are present in this reaction. So again, obviously it's probably started at this point, but have we already reached the point where we hit equilibrium or not? And again, which way we need to kind of go to reach equilibrium. So obviously in this problem, they would give you, say, the K value in this problem so that you could compare it and stuff like that. Any questions on that?
I have a question. So for the initial concentrations, is that value is going to be different than the concentrations that were calculated in the K value? Is that what's happening?
Yeah, so the idea here is if you're given the initial concentrations, and again, they may actually tend up being the equilibrium concentrations as well as possible. It's just the fact that you're not sure if it is the equilibrium concentrations or not, or your system's at equilibrium. So because they've given you pretty much, say, amounts of this guy, this guy, this guy, and this guy, you're not sure if that's already hit equilibrium. So you could use this to determine, are you there yet? Or if you're not there, which way you need to go. So it could end up being initial sort of concentrations of everybody are not really at equilibrium, and it needs to either make more products to get there or more reactants to get there. Or you may do the calculation and go, oh, my Q value and my K value are the same, which means, oh, this system's already at equilibrium. It doesn't need to go either way to reach equilibrium because we're already there. So that's sort of what basically we use kind of the reaction quotient for. It's really a way for us to determine, because we're not 100% sure we've already hit equilibrium. It's a way we could figure out if we did hit equilibrium, and more importantly, if we didn't, sort of which way we need to go to get to equilibrium, either make more products or more reactants.
Okay, thank you.
You're welcome. Other questions? Okay. So why don't you try one here and see what you come up with? So we got this reaction, we got some moles of everybody, we got some volume, we have the K value given to us. So first off, decide whether or not this is at equilibrium. And if it's not at equilibrium, which way we need to go to reach equilibrium. So take a couple of minutes and see what you come up with. So in this particular case, we have the moles of everybody. So we've got the moles of our N2, our H2, our NH3. We also have the volume given to us. So we have the moles and the liters. So that allows us to get the molarity of everybody. We have the K value given to us. And ultimately, we're trying to figure out, again, is the system at equilibrium? So this is definitely where Q is sort of involved. Q would equal, again, exact same way we would do our K. So it'll be our products. Again, we want to also square it because of the coefficient. We want to divide it by our N2 and our H2, which also needs to be cubed because of the coefficient. And ultimately, we're going to look at that and compare that to the K value that was given to us to determine whether or not the system is at equilibrium. So the first thing that we want to do is figure out our concentration. So we'll start with the N2 here. So if we take the moles of our N2, which looks like 0.249 moles divided by 3.5 liters, that's going to give us something like 0.0711 molar. If we do the same thing for our H2, taking the moles that was given to us, 0.0321 divided by 3.5 liters, the volume's the same for everybody because they're all basically floating around in the same container, right? Gets us something like 0.00917. And lastly, our NH3, 0.0000 642, I think, moles divided by 3.5 liters, going to get us 0.000183 molar. Any questions on how to calculate the molarity there? Okay. So Q, again, as we saw on the previous slide there, going to be NH3 squared divided by N2 and H2 cubed. So now that we have all these values, we could basically plug it in there, 0.000183 and squaring it, divided by our N2, 0.0711 and 0.00917 and cubing it, looking like we're going to end up with something like 0.611 as our Q value. First off, any questions on that part of the calculation there? Okay. So now that we have the Q value, we want to also use the K value that was given to us in the particular problem. So the K value was, I believe, 1.2. Our Q value is 0.611. That means in this particular case, Q is less than the K value. That first off tells us that we are not at equilibrium. And second, because Q is less than K, it needs to go in the opposite direction towards the product side. So we need to make more products. Our head to the right, right? Question on that? Question on where any numbers came from or anything? So this I would classify as a really sort of straightforward Q type problem where that is ultimately what you're trying to figure out. So if you come across a problem where it says, hey, is this system at equilibrium? And if not, obviously which way you need to go. It's sort of probably 9 times out of 10 how you will use Q. We will see a little bit later on in this chapter another place where you should use Q and what it could affect, and we'll talk about it when we get there. But this is sort of a straightforward sort of Q example. Any questions on any of those steps there? Okay.
So for this problem, the temperature doesn't matter. Like we don't need to use that for any of the equations, right?
It really doesn't matter the temperature in this particular case.
Okay.
Again, sometimes they'll give you some of those extra pieces of information that's not necessary to solve the problem in this case. Other questions? You know, if there was like a second part to this problem where it asks you, what is the KP value, then you could always use the temperature with that formula that we saw earlier and stuff like that. Other questions? Okay. Before we go too far into the next topic, let me just go back and let's take a look at an example of sort of what we were talking about, using different equations and sort of manipulate them just to make sure everybody's on the same page. So let's say we wanted to know what the K value was for this particular reaction here. Given that you started with, we'll go with, actually, let's do this. Yeah, let's do. Oops. Go with 25. And let's do and we'll do K as 5. All right, I just made up these numbers. So why don't you give it a go? So based on these two equations here in the box, use these two to figure out what the K value is for this equation up on top. So see what you come up with. I'll do it as well since I just messed it up and changed it from what I was going to do, and we'll hopefully get the same answer. So take a minute or two and see what you come up with. So this is kind of like what we were talking about earlier, about manipulating the reactions. Law type problems. This approach is just to keep it simple and try to get everybody kind of on the right side or the correct side that it needs to be. So for example, if I were looking at this, I would see 2NO. I see NO over here. The NO is on the correct side of the arrow. It's on the left-hand side, but there's not two of them. There's only one, which tells me I probably need to take the top equation and multiply the entire thing by 2. And if I do that, I end up with 2NO plus N2O2 as a half times 2 is 1. Now, the important difference, though, between this and Hess's law is the K value, as we talked about. Because we multiplied by a common number of 2, we're actually then going to square it up there on top because of that. Any questions on that? I then would look at perhaps O2 here, and I see O2 over here, and it's on the left-hand side is where I need it. It's on the right-hand side and the bottom equation. So this guy, I need to reverse the bottom equation. So what that means is my reactants become my products become the reactants, and I end up with something like this. Now, because I reverse this reaction, we don't change the sign like we do in Hess's law. It becomes 1 over the K value in this particular case because we reversed it. Any questions on that?
Why would you reverse it again? Could you go over that one more time? Sorry.
Yeah, so I already sort of took care of the NO here on the first equation, right? So kind of the next thing I'm looking at is O2. And I see O2 in the equation I'm looking to get to is on the left-hand side. On the only equation that has O2 here on the bottom, it's on the right-hand side. So I basically need to reverse it to get the O2 to the correct side. In addition, if you look at the NO2, it's actually on the wrong side as well. The NO2 actually has to get to the other side as well. So by simply reversing the bottom reaction, that gets everybody sort of to their correct sides. I won't say right side, but correct sides of what we're looking for in our sort of desired equation over here, just to make sure everybody's on the same side.
Okay, so you're just flipping it, like nothing's changing in the sense of like the formula or the equation itself. You're just flipping it.
Right, we're just basically reversing the reaction. And when we reverse a reaction that's an equilibrium reaction, the equilibrium constant is affected by taking 1 over the K value. And that's because if we wrote the K value for the bottom one the way it's written right now, it's N2O2 and O2 divided by NO2 squared. When we reverse it like we have on the bottom, if we write the K value, it is NO2 squared divided by N2O2 and O2. And this is really the way we want it, like we have it on the bottom. And the difference between how it was to how we changed it is it's basically 1 over the K value. So it basically flips it around because our reactants become our products and our products become our reactants. Now that we have everybody on the correct side, we could add both of these together. Anything on opposite sides of the arrow that are the same could either cancel out completely or reduce. And if we do that, we get 2NO plus O2 gives us 2NO2. Now, remember here in the K values, we'll just get some numbers here. So that's going to be 25 squared up there up on top, it looks like. So that's going to be 625. And 1 divided by 5 going to be 0.2. So to get the K value now for our overall reaction, we're going to multiply those K values together. So 625 times the 0.2, not add like a lot of people like to do. We're going to actually multiply them and ends up with something like a 125 would be the K value for our sort of reaction that we're looking for. Any questions on that? Okay. So I just want to make sure we kind of went over an example with real sort of things here. All right, any questions on, again, this, our Q that we just talked about, reaction quotients? Okay. All right, so last thing we're going to lecture on here for lab here during this time is we're just going to get into equilibrium. We're going to go through a problem together so you understand it. And then tomorrow that will set us up for lecture good to do more examples and make sure everybody's sort of on the same page. So let us go and talk about that then. Okay. So let's talk about solving actual equilibrium type problems. So when we solve equilibrium problems, a lot of times what we are given to start with is not the equilibrium values of, say, concentration or pressure or whatever it may be, which means if we want to sort of figure out K or something like that, we can't just go into the equation and stuff like that. So a lot of times what we're given is sort of initial concentrations, and we want to figure out when the system reaches equilibrium, what is everybody's equilibrium concentrations going to be? So the very common way that we do that is we use what is referred to as an ice table to do that. Now, you may have used ice tables before. You talked about them probably super briefly if you took Chem 3 at Saddleback in like chapter 17, the very last chapter, probably on the last day or 2 days of class and stuff like that. And you've done ice tables maybe before. Occasionally, depending on maybe who you had for 1A, you might even use ice tables to solve limiting reagent type problems and those type of things. So you might have seen it or you might not have seen it. So we're going to talk about obviously sort of how to do it, how it works here in just a second. But basically what ICE sort of stands for, I is initial. So this is like the initial concentrations, initial pressures of everybody. C is the change. So this is basically, you know, how the reaction is changing. So how much products are being lost, how much how much reactants are decreasing, how much products are increasing. And E means equilibrium. So when we do these type of problems, we typically do ice tables, and you want to make sure you do show the ice tables, and we're going to do one together here in just a second. But we use it to really figure out what our equilibrium concentration is going to be. And this calculation we're going to talk about here is a pretty important one. It's pretty much the entire calculation done over and over again in a lot of chapters that we're going to talk about with some slight things that are changed. So you really want to make sure, obviously, you understand sort of what's happening here. So usually it starts with a balanced equation. You want to make sure you have your initial concentration. So usually you want to figure out the molarity of everybody. You could also do it with pressures. And if you do an ice table, this is sort of what I was talking about earlier. If you do an ice table, you want to make sure that probably the concentrations and molarity. And if you're dealing with a pressure, you want to make sure that those guys are in atmospheres. Again, even if they give you some other unit and they ask for some other unit, when you do the ice table, the pressures should be in atmospheres in order for it to come out correctly. So you're going to do the initial concentrations. We're going to represent the change with an X. You can use any letter you like, but most people use X. And we try to keep it to sort of one unknown. Otherwise, obviously, it becomes a little bit hard to sort of solve for. We then kind of go through the ice table. We use our equilibrium expression to solve for X. And when we do, we could then use X to figure out how much is there at equilibrium for everybody when it's all said and done. That's a lot of words, may not make sense to you. So I think it's best to actually see it sort of happening. So let us do the next example together here. And we're going to go through it just to make sure everybody understands sort of the different processes that are happening here. So in this particular case, we have this reaction, which is Br2 goes to 2Br. The K value is 7 in this particular case, and the initial concentration of Br2 is 0.663. We want to calculate what is the equilibrium concentration of everybody here when we reach equilibrium. So the first thing that we could look at is we could write our equilibrium expression for this, which is our K is equal to Br, and again, we want to square it because of the coefficient, divided by Br2. The next thing that we want to do is really set up our ice table, and our ice table is set up basically by using the balanced equation. And we're going to start with our initial entry. So our initial entry is we have 0.663 molar Br2. Now you'll see in this problem that they do not mention anything about Br in here. So in this case, when they only give you the starting amounts of your reactants, it is probably safe to assume that this reaction is going from reactants to products. And it's also safe to assume that you are starting out with 0 in terms of your products at this point. So since they didn't give us any information about our products, it is safe to start with 0. It is also, like I just mentioned, probably safe to assume that you're going from left to right, from reactants to products. Also, you would not calculate Q in this case because you can't. You don't have any information about your product, so you can't even calculate Q or anything in this particular case. Any questions so far on this? The change part is really the important part. The change part does two things. It will allow you to figure out how much is being sort of lost by one side and gained by the other. It also takes care of all the stoichiometry for you, the mole-to-mole relationships and all that kind of stuff when you do the change part. So the change is going to be represented by X. And since we are assuming that this reaction is going from reactants to products, we would imagine that over the period of time, the amount of Br2, which is a reactant, should start to decrease. The amount of Br, which is a product, should also start to increase. And the way we represent that is with minuses and pluses in our ICE table. So for our Br2, this would be minus X. Minus because it's a reactant. We're assuming it's decreasing with time. X is sort of the unknown at this point. And by the way, the coefficient here is 1. And that's why it's just minus X in this case. When we get to the product side, we should be expecting our Br to be increasing. And this would make it a plus on this side. And it would be plus 2X. The 2 here is for the stoichiometry part of it, the mole-to-mole relationship. Super important to make sure that you include that. Otherwise, you will definitely get the wrong answer. So the change part, you want to use X's. You want to use minuses and pluses, and you also want to take the coefficients into account because, again, when you do that, that is essentially taking care of all that great stoichiometry everybody loves, mole-to-mole relationships, and all those kind of things. Any questions on the change part of the table? Okay. So when we now get to our equilibrium part of the table, we're just going to simply carry everything down. So at equilibrium, we would take our 0.663, which is like our initial concentration, and then we would minus X, whatever that change is going to be when this thing goes through equilibrium. And for our product side, we have basically 0 plus 2X, which is basically just 2X. We're just going to be gaining. So this is what this sort of ICE table should look like in this particular problem. Any questions on any part of it, what anything means? Okay, so I think maybe that question, I'm looking now in the chat box, was from the previous one. So if it was from the previous one, I'll just let you know that it was squared and not multiplied by 2 because that's what happens when we multiply our equilibrium constant value by a common number. We take it to that power. So I think that's what it's referring to. Okay, so now that we have this, basically it really does become a math problem at this point. We need to figure out what X equals, right? Because ultimate goal is we want to figure out what these numbers actually are at this point. So to do that, we're going to use our equilibrium expression that we have up here. So we're going to take our K is equal to the BR squared divided by the BR2, and that's going to equal 7. Putting in our values here, that's going to give us 2X squared divided by 0.663 3 minus x, and that's going to equal 7. So all I did at this point, just so we're clear, is I took everything on my equilibrium line here and basically put it into my equilibrium expression. So I basically just pop those guys into there. Any questions on that so far?
I have a question. So for the change, is it always gonna be x, or is there gonna be equations where like those change values will be given to us?
Yes. So there's going to be both as we go through multiple chapters and stuff like this. So this calculation that we're doing is sort of the main calculation for this class. We kind of use it in a lot of situations. And in a lot of situations, we do sort of tweak it a little bit, kind of change it just a little bit. So in a lot of cases, it will be like what we're doing right here, where you don't know what the change is, but there are going to be a number of problems in later chapters, like in chapter, say, 15, 16, something like that, 14, maybe even, that we will actually know what the change is, and we'll actually use numbers. And we'll talk about those as we go through those different ones. So kind of yes to both of your questions. It kind of will happen like this, and there will be definitely situations where you actually know, or you should know, what the change is from the outset of the problem.
Okay, thank you.
You're welcome. Other questions? Okay. All right. So now that we have this, again, like I said, it does become sort of math at this point. So we're going to solve this, and let me go here. Let me flip it to the next page so I have more room. So what we got going so far is 2x squared divided by 0.663 minus x equals 7. We're basically going to multiply the bottom to the other side. And if we do that and square the top, we're going to get 4x squared is equal to 4.641 minus 7x. So I basically multiplied the bottom to the other side. At this point, we could kind of combine everybody to the same side. So this is going to be 4x squared plus 7x minus 4.641 is equal to 0. Perhaps you recognize this from math, maybe. This is what is referred to as the quadratic sort of equation or formula, right? Kind of has that quadratic formula. So a very common way that we need to solve these problems is to use something like the quadratic formula. So to remind everybody, that is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So a couple of things about our quadratic here. You obviously do get two answers when you use the quadratic formula, one where you do the positive and then one where you do the negative. And as we will see shortly, in certain cases, one of those answers will not make sense. The other one will make sense. So this is a very common way that you need to solve this. Looking at our equation, this would be A, this would be B, and this would be C, including the negative would go with it as well. So that's our A, B, and C. So if we do that and we put that into our sort of formula here, we get x is equal to minus b, which is minus 7, plus or minus. And if we put the numbers into the square root, so that's going to be b squared, which is 7 squared, minus 4 times a in this case, which is 4, times c, which is negative 4.641. And if you do all that inside the square root value, you get something like 123.256. Then if you take the square root of that, you end up with like 11.1 basically. So if you take the square root of it, 11.1. all divided by 2 times A, which is 2 times 4, which is 8. Any questions on that part of it so far? And again, we're doing this to basically get our X value from our table. So we could actually figure out what our concentrations are. All right, so at this point, if we get 2 X values. So the first X value I'm going to do by adding. So I'm going to take -7 plus the 11.1 divided by 8 gives us something like an X value of 0.513. I'm going to do the subtraction part now. So -7 minus 11.1 divided by 8 gives us something like minus 2.263. So these are our 2X values, and that does happen. When you use the quadratic formula, you should always get kind of 2 values. Any questions on that so far? Okay. So I'm just going to kind of rewrite the ICE table from the previous page there, just to make sure everybody sees where we're going next. So initially 0.6630 minus X plus 2X equilibrium 0.663 minus X and 2X. Any questions up to that point there? Okay. Now, when looking at these 2 possible values for X, you will always end up with one that does not make sense. So just looking at what we're going to do with those X's is we're going to take them and put them back into these 2 things. Now, clearly, one of the things we're going to do is take 2 times X, which means if I take 2 times minus 2.263, I get something like minus 4 point something. You cannot have a negative concentration, which tells us this is not a good value of X. So you cannot obviously have a negative concentration. So what that means and what that tells us is that the actual correct value for X should be this 0.513 number. Any questions on that? Also, if you if you put it into the first one, it's okay. But if you put it into the second one, 2 times that negative, going to give you negative concentration, which you cannot have. So what that now allows us to know is this is the X value that we should put into here and also into here. And if we do that for our BR2, we end up with 0.663 minus 0.513. And that will end up with 0.663 minus 0.513, 0.150 looks like. And we do need a unit, so it should be molarity here because we are looking for the unit of concentration. And we would put that in for our other one as well, which is BR. BR would equal 2 times X, which would be 0.513. And that's going to be 2 times 0.513, 1.026 as our second concentration here. And what these guys would represent is the equilibrium concentrations of both of these. So at equilibrium, we are going to end up with 0.15 molar BR2, and we're going to end up with 1.026 molar BR. And this makes sense based on what we see in our ICE table. We started with 0.663, the change was 0.513, and we end up with a little bit less amount of what we started with, a BR2, and we increase going from 0 to 1.026 or 1.03 if you round that. And we do see an increase in our product formation, which is what we would expect considering that the equilibrium constant is 7. This reaction is probably heading in this direction. We should see that increase in products, decrease in reactants. Question on that there? Now, the nice thing about math is it's math, which means you can make sure or kind of check to make sure everything's good. So how could you check this to make sure you didn't screw up anywhere along the way? This is a relatively simple sort of quadratic formula, but there's a lot of places where there's a lot of factoring and that type of stuff happening that, you know, you could mess up something, forget a zero, add a zero, you know, those type of things are very common mistakes that people make. So what you could do at the very end, if you have time, is now that these are the equilibrium concentrations, you could actually put it back into the equilibrium expression. And if we do that, we would end up with 1.026 squared divided by 0.150. And if you did everything correctly, it should come to about 7, which it does, 7.02-ish, which is about 7, right? With rounding, it should come pretty close to that. So the nice thing about it is you could actually sort of check your calculation at the end by putting it back into the equilibrium expression once you've determined the equilibrium concentrations. And you can see that you should end up obviously with the same value for K that you started with. A little bit different probably with some rounding, but should be definitely in the same ballpark. Any questions on any of those steps along the way? Much like a lot of things, it does obviously start with a balanced equation, which in a lot of cases, you'll probably be given the equation, so you don't have to worry too much about that. But places where people really do kind of error when they're doing these things is in this area. They forget about the coefficients, so they have the wrong mole-to-mole relationship. Also, again, this one's not too difficult, but sort of the factoring part and getting to this quadratic formula, a lot of people sort of mess up on that part. So you just want to make sure you take your time and you should be hopefully okay. Any questions on any part of it? Again, this is definitely a calculation that you will see over and over again in this class, and it's something you do have to master. Otherwise, you will be in trouble in other chapters because, like I said, we'll continue to kind of use this type of calculation, but do some variations on it. So you want to make sure you really understand sort of what's going on here. Any questions on any of that there? Okay, so that's probably enough torture in terms of the lecture part of it for now, I think. Any questions on anything we kind of talked about here in lecture part here?
For quick question. So for the initial value, if the balance equation has more than one item, so then would the values be multiplied for the initial value, or would they just be added? How would that work?
So are you asking like if this guy had like a 3 or something in front of it?
I'm like saying like if it was like the equation had more components to it, so like BR2 plus something else equals.
Yeah, so your ice table would just be a little bit bigger. So you would have another column next to it, for example, and you would do the same thing. Yeah. And so, for example, you would have something here like say 0.17, you know, minus X or something like that. And then that would also get incorporated down here because you would have another value here. So it makes, that's the part where you will get into some problems where, you know, when you have multiple reactants, for example, you'll do some factoring and, you know, you have to kind of distribute things. And that's where a lot of the math, you know, does get a little bit complicated in that sense, or areas where people sometimes will make a mistake in that part when you get into, you know, a couple of reactants, maybe even a couple of products where you have to do a lot of, it's really just math, algebra and stuff like that. But there's a lot of places where, you know, sometimes extra zeros get lost and stuff like that. But to answer your question, if you had multiple reactants, you would obviously fill in the ice table underneath that one, just like we did for BR2, and it would be incorporated into everything else along the way.
Okay, thank you.
You're welcome. Other questions? Okay, so like I said, that seems like a good amount of torture here for lecturing, I think. So what we're going to do, I think, is why don't we take why don't we come back at 3? We'll take a 20-minute break. And that way we could stretch, stand up, and all that good stuff since we had double lecture here. And we'll talk about the activity, which is the Excel activity. And what I'm going to do actually is I'm going to end this meeting right now, so I don't have to do so much editing, and we'll restart a new lab meeting at 3, and that way I could just post a lecture here without having to cut out all the rest of the stuff and that type of stuff. So we're going to end the meeting for now, but we'll call it 3 o'clock. We'll come back and we'll talk about the activity and the Excel, and then we'll wrap it up. Probably not too long after that. All right. Any questions on anything like that?
Professor,
Yeah.
Where do you post the recorded lectures?
They'll be in the module section. So now that we actually have some actual lectures,
Okay.
so next day or so, there'll be something that'll pop up. They'll say like recorded lectures, and it'll have like the date, and you could click off of there. You could either watch it through on Canvas through the thing there, or